differential equations. Section 9.2, direction fields and Euler's method. We learned that for most of the differential equations, it's impossible to get the solution through the explicit formula. Despite the absence of the explicit solution, we can still learn something about the solution through some approximation. We may use a graphical approach, which are the direction fields, or we may use the numerical approach, which is called Euler's method. And in this video, we will talk about the Euler's method. We do remember nice blue line segments, which represents the slope. We remember from the previous video. That means that they called direction fields or the slope fields, and they help us to visualize the general shape of the curve. And if we will nicely follow, if I will draw a curve like parallel to nearby this line segments, I can get the solution. Of course, respecting the initial value information that my curve must go through the point 0, 1. And as we can see, we nicely follow the direction because the line segments indicates the direction in which the solution curve is heading. That means that's definitely, we remember that was the output from the direction fields. That means we do have a graph, we have a graph of the solution. We still don't have the explicit formula, but having a graph, having a curve is I think it's a nice solution. Okay, that's direction fields. Now, what we can do? Of course, the basic idea behind the direction fields can be used to find a numerical approximation to the solution of the differential equations. That's what we can try. We will try a little bit different method, which we know is called Euler's method. But let's see, numerical approximation. Let's take the same equation, y prime equals to x plus y at 0 is equal to 1. Then what we can do? We can try at this point, because we have a point given, and in fact we do have a slope. Using the point slope form, I can get a tangent line at the point 0, 1. I can use my linear approximation. And we do have the equation of the linearization, x plus 1. And using the linearization, I can approximate some values. But let's walk through that equation. Let's obtain this equation. Okay, that means we do have the pink curve is part of the solution that we get through the direction fields, and the blue line is a tangent line. That means let's see how I got this. That means let's say my first point will be I am investigating the tangent line at the point 0, 1, and I can possibly call x sub 0, y sub 0. We know that the slope of the tangent line at this point will be y prime, which is defined as x plus y, 0 plus 1, 1. Okay, and now let's just use point slope form. Y sub 0, y minus y sub 1 minus y sub 0, and then slope x sub 0. So I can put my point. Of course, slope, right? Slope will be, okay, I can put y prime, and then I can actually keep this, and let's substitute. My point is 1, slope is 1, and my x value is 0. So we do have a tangent line. 1 times x is x plus 1. Okay, 1 plus x. That means blue line has the equation x plus 1. And now, if I would like to approximate some values near, of course, near the point x0, because we will look at the horizontal shift. 0.0, like let's say 0.25 maybe, I can use the blue line because I don't have the explicit formula for the ping. And I think it's quite good. It will be quite good approximation. It's quite close. However, if I would like to go a little bit further and approximate, the blue line, it will be not as helpful, yeah, because we can see the difference between the curve and the blue line. It's getting bigger. That means what we can do, we can stop at some point. Let's say we will jump by 0.5. That means we can stop at 0.5 and find another tangent line, another slope, like how the function is changing. That means we will stop here. Of course, to get the value at the 0.5, I will use the blue tangent line. That means the blue tangent line is telling me that if I substitute 0.5, I will have 1.5. Okay, but let's see, let's do it again. That means now I'm looking at the tangent line at the point I switch my x from 0 to 0.5. That means I'm going, and we will call the step size is 0.5, and substituting 0.5 to the blue line, 0.5 plus 1 is of course 1.5. Okay, that means that's my new values. And I can say x sub 1, y sub 1. x1, y1. Okay, and let's find. That means now the new slope at the point 0.5, 1.5 will be still the derivative, which is defined as x plus y. Half plus 1.5 is 2. Okay, that means this is the new slope, and I think will be that yellow line. Okay, let's find out. Now we do have to compute y sub 2 minus y sub 1 slope x sub 2 minus x sub 1. It means the approximation or the line, the next y values will be defined as a previous y value. That's the slope. That means I can put the slope, and this will be the actually the step size. Let's define this. The second, this is the blue one, the first one, the second tangent line, it will be y value plus the slope and x sub 2 minus, and now we are at the 0.5. Okay, that means this one I can of course simplify, and I will have 2 times x if I would like just to use x. 2 times half is 1, negative 1, 1.5 minus 1, it will be positive half. Okay, so this is the second tangent line, which is this one, 2x plus 0.5. Okay, and I can, of course, I can keep working, because now using that second line, let's say I would like to approximate the value at 3/4. That's somewhere in the middle. Then I can use this line, and it's still fine. And we still have some error in this approximation, but that's the approximation. But when I will go again further away, even for 0.1, for x equals to 1, getting the approximation, it's still okay, but a little bit further, I will have not good approximation. That means what I can do, I can again stop at 1, which means I am moving by 0.5, because I move 0.5 units, and then I'm going again by 0.5, and we will call this h. Okay, that's the step size. And then at this point, I can compute another tangent, and then I can use that tangent line as an approximation. I mean, let's maybe do one more. I mean, at the point, and I can approximate this point. If x is 1, I can use that line, 2 times 1 plus half. 2.5. Okay. And let's see what we have. This will be our second, right? That means I can say this will be, oh, we actually, maybe we can use different color than blue, maybe purple, x sub 2, y sub 2. That means y minus y sub 2. That means I'm creating the third tangent line, and then slope x sub 3, x sub 2. Okay, that's my point slope form. It means the third tangent line will be the second, the one y value before, plus the slope, that's the slope, and this will be the difference, which is actually kind of like the step size. And let's substitute the value. The value of the y coordinate is actually 2.5, okay, plus the slope. Oh, we didn't compute the slope. Slope at this point will be the same thing, y prime x plus y. 2.5 plus 1, it will give me 3.5. 3.5, and then x, which of course is the next one, minus 1. Which means my third tangent line will be 3.5x, 3.5 negative minus plus 2.5 will be 1.5 negative. Okay, that means this is another tangent line, which I don't, but we can see the slope is steeper, of course, because follows our solution curve. 3.5x minus 1.5, and negative the y-intercept, because probably it will be steeper and will intersect y at the negative point. Okay, that's we can see that's how we can approximate, and all of the boxed equations are the tangent lines. That means that's how we can use and approximate. So let's look at this, and we can of course approximate the corresponding y values. Right? Let's look at one more time. That means probably if I would like to approximate the value of the function at 3/4 here, yeah, I will use that tangent line. I can just substitute 3/4. Let me use this. If I would like to get the approximation maybe for 1/4, okay, I will use the blue line. Or if I would like to get the approximation for 1.25, somewhere here, I will use the third one, because using the previous one will be not as accurate as this one. We can still improve this approximation, and our jumps, our step size could be smaller. I choose 0.5, 1, 1.5, but we can use like 0.25, or we can use 0.2, we can use 0.1. Yeah? We will do some approximation, maybe 0.1. Okay, that means this is, but let's formulate and let's get the nice systematic rigorous formula for the Euler's method. That means let's see how this looks like. I think this, I mean, I can pick any, but maybe I have enough room here. Do I have room here? No. That means I can possibly, what color? Green. Let me pick this equation, okay? And let's see how we can compute. That means in order to get the value, to approximate the value for y, like a certain y point, okay? We have to know the one y value before. That means y sub 2, we need the y sub 1, of course, because we know we are at a certain level and we need this y sub 1 plus, and this is slope, plus the slope, because slope is the rate of change, how the curve is changing. That means y value plus the rate of change, but we are affected by this difference between x. That means we are always affected by this step size. That means this quantity we will call h, and this is step size. This is, of course, slope, y prime, and this is just the y value, right? Just the value, the previous one, okay? And we adding. As we can see, y value, the one before we had it, and plus the slope times the step size. Okay, and that's actually the Euler's method. That's what we did, and we can see everything is based on the tangent line. I mean, let's see. This is, of course, that's a little bit of description about the Euler's method, but let's look at the formulas. And that's the formula. Don't be scared. I can explain this. The Euler's method is for the general first order initial value problem, y prime equals to f of xy, and the initial problem is at x sub 0, the function is defined as a y sub 0. Our aim is to find approximate values for the solution at equally spaced numbers. As we can see, we're starting at the x sub 0, and then we're going to x sub 1, x sub 2, right? We can see x sub 0, x sub 1, but we will jump by h. And that h we call step size. Okay, that means x sub 0 plus h. We are at x sub 1. X sub 1 plus h will be x sub 2, and so on. The differential equation tells us that the slope, of course, is that, that function, y prime equals to f of x sub 0, y sub 0. So we know we calculate this. The figure shows that the approximate value of the solution when x equals to x sub 1 is, and we recognize this, that means y sub 1 will be defined, y sub 1, which is this one, will be defined by this value. Yeah, we can see y sub 0, this, plus this. And this is just the slope affected by the step size, h times the slope. And the same we will keep working. We can see if it's 2, everything is related to 1. That means in general, when we have to define the nth tangent or the nth approximation, the y sub n, then we will need the information 1 before, y sub n minus 1, still the same step size, and the slope related to that point, because we can see that's the slope. Right? That's we can see that's the, this will be, this is just the y value, and then the step size, I can just write like that, that's the step size times the slope, of course the corresponding slope. Okay, that's how we can compute. So let's take this formula, and that's it, that's actually the Euler's method, Euler's formula. Let's take it and let's compute the same things what we just did, but now the step size are 0.1. So we will need a little bit of arithmetic, but probably we will do it. Use Euler's method with the step size 0.1 to construct a table of approximate values for the solution of the initial value problem, y prime equals to x plus y, y at 0 equals to 1. That means if x is 0, y is 1, the slope is defined as a x plus 1. 0 plus 1 is 1. Okay, we did this one. Okay, now that means this is actually y sub 0. I can write this. Y sub 1 will be defined as a y sub 0 plus h times the slope. But how can I write the slope which was defined at this point, the previous line? Okay, and this is of course the slope. Okay, as we can see, we will get that value 1, okay, 1 plus 0.1, and the slope is 1. 0.1. Okay, which is 1.1. 1.1 plus 1, 1.1. That means this is my the first value. I did approximate the value when x is equal to 0.1. The value of the function, of the solution, is 1.1. We can add these two values. I can add 0.1 plus 1.1 and get the slope. 1.2. Okay. Now let's do the same for the second. Y sub 2 will be the value of y sub 1 plus h and the slope at that point. That means this is 1.1 plus step size 1.1 times the green slope. And maybe use colors will be easier. Okay, 1.1 plus 0.12. It will be 1.22. Okay, 1.22. And now, maybe blue color, adding x and y, we will get the slope at the point 2. X sub 2, y sub 2. 1.42. Okay, that's we do have a table with the slopes and with the value. Okay, let's keep working. Y sub 3 will be y sub 2 plus h, the step size, and slope at the second point. Y sub 2, y sub 2. It means my y2 will be 1.22 plus 0.1 times the blue slope, 1.42. And when I move the decimal point and add together, it will be 0.142. When I add together, it will be 1.662. Right? 6. Am I right? No, 1 point. Wrong, that's the slope. We can actually do this. I can put 1.22 and 0.142. 462. No, something is wrong. Let's do it again slowly. 1.22 plus, that's 0.142. 2631. Okay. 1362. Okay. And now adding them together, maybe purple, adding this one and this one will give me the slope at that point. So we can see the slope is increasing because we know the solution curve. Oh, when I add this, this will be 1662. I hope I will not make more arithmetic mistakes. Okay, let's keep working. We do have 2 more because then we can practice. Okay, y sub 4 is defined as a y sub 3 plus the step size and the slope at the point x3, y3. This one is 1.362 plus 0.1 times the purple, 1.662. Oh, another arithmetic. I will put this 1.362, and when I take the purple value 1.662 multiplied by 0.1, the decimal point will go to the left. 2.825, because it's 4 and 1, 5 and 1. Okay, that means this value is 1.5282. Okay, now I have to add what color I can use. Maybe, okay, maybe this one. This one, x plus y, will give me the slope. at x4, y4. And just for that, means this will be 1.9282. Okay, one more. But then, computing this, we will know perfectly the Euler's method. And one more, still red, y sub 5 will be y sub 4, that's when we need the value above, plus the slope affected by h, by the step size. And this will be at x4, y4. I need this value 1.5282 plus 0.1 times the yellow or golden 1.9282. And let's see what we will have. We will have 1.528 1.5282, and the yellow number multiplied by 0.1, I will again move the decimal point, 19282. Let's add together 2, 0, 1, 1, 1, 2, right? Oh, can I do this? 1, 7, 1. Okay, 1.72102. Okay, and then we can add together and we can have a slope. Let's finish here. That means I believe this is the correct value, because actually the last value which, what color? Actually, I can keep the red. 0.5, and this one, of course, will give me the slope, but value of the function at 0.5, we've got approximation 1.72102. As we can see, it's a little bit better approximation, because if we remember, I can switch the slides. Do you remember this one was just 1.5? 1.5, the value of the function, but using, of course, just the first tangent line, first linear approximation, which is not as accurate as I will jump by 0.1 if my step size will be smaller. That means instead of 1.5, I have 1.7, a little bit higher, and I believe this is better approximation. If we will switch, if we will change the step size for 0.01 maybe, it will be even better. Okay, that's the way to approximate. Please practice and please make sure that we understand this method. Let's see, that's a little bit of solution. And I also have from your textbook, when more values is still the value of the function, approximating the value of the function at 0.5, and using the step size, that's what we did at the beginning, just 0.5, the value will be 1.5. We did this one, right? The step size 0.1, that's we've got this value 1.721020. But if you will keep changing the step size, actually decreasing, making smaller and smaller, the approximation will be even more accurate. Okay? Of course, still thinking that we don't have the explicit formula as a solution. Okay, that's some ideas. And let's solve two problems and we will be done. Okay, consider the differential equation dy dx equals to 3x minus 2y. Let's y be a function g of x and be a solution to the differential equation with the initial value g at 0 equals to k, and k is just a constant. Euler's method, starting at 0 with the step size of 1, gives the approximation g at 2 equals to 4.5. Find the value of k. So you can see we will use the same, we will use the Euler's method and try to find out what k is. That's we will start, okay, x and we have to start at 0, and then y. Okay, y. Let's see what we can get. That means when x is 0, we can see this. When x is 0, the solution y is k. That's nice and easy. I need a little bit more space for calculation. Oh. Okay, a little bit more. Okay. And we will go, step size is 1. That's we will go x1 and actually x2, because we will stop at 2. We have to figure out what k is, and we have this value. Okay, that means x is 0, k will be the y value, the corresponding y value. Then we can compute, I can keep this, we can compute dy dx, slope, right? That's the slope. We need the slope in order to get the other values. And slope is defined as a 3 times x minus 2y. 3 times 0 minus 2 times k, which is actually negative 2k. Oh, a little bit slopey. Okay, negative 2k. Okay, that means the next y value will be the value before plus the step size, but the step size is 1 times the slope, negative 2k. Okay, we remember from previous exercise. And this will give me k minus 2k, negative k. Okay, and then again, the slope will be 3 times x, which is 1, minus 2 times the y value, which is negative k in this case. 3 plus 2k. That's the slope, the new slope, when x is 1. And then one more. To get the y value, which corresponds to the x2, we have to take the one value in front, which is negative k, plus step size, which is 1, times the previous slope. 3 plus 2k. And then we will have 3. 1 times 2k, 2k minus k is just k. Okay, 3 plus k. And what we know, I mean, I can still compute slope, but of course I can stop here because this is telling me that g at 2 using my k value is 3 plus k. Also, g at 2 was given to us 4.5. So we have a nice equation, 3 plus k, it's equal to 4.5. K is simply 1.5. Oh, we can see we did solve it. Great. Excellent. And one more. And we did use the Euler's method. The same thing. Consider the differential equation dy dx equals to x minus y minus 2, and the initial condition f of negative 1 is 3. Use the Euler's method with 3 steps of equal size to approximate f of 2. As we can see, jumping from negative 1 to 2, probably we have to say that the step size is simply 1. We will go by 1. And we will actually have 3 steps. Okay, let's do the same thing. X and y. We will start with negative 1. The solution at negative 1 is 3. Oh, we will need more computation. Yes, we will need more computation. Okay, because we will go by 1. 0, 1, and 2. And we're looking for this value. Using the Euler's method, we can nicely reach this. Okay, I need a little bit of room. I will leave it here. And we will need slope because we know the tangent line, the slope, to approximate this. The linearization. And slope is defined as a x minus y minus 2. Okay, that means let's compute this slope. this slope will be defined x minus y minus 2, and this is just negative 6. Okay, now let's compute the next y value. I have to copy the value above plus h, which is in this case the step size. Step size, it's simply 1. 1 times the slope above, negative 3. And computing a new slope, x is 0, minus y, negative 3, minus 2, positive 3, minus 2, it is 1. Great. Am I right? Yes. Okay, now another. Computing the y value for x1, I need the y value before, the one above, step size 1 times the slope 1. 1 times 1 is 1, negative 3, negative 2. And let's see, 1 minus negative 2 minus 2, positive 2, negative 2, 0, 1, again 1. Oh, that means we can see the solution curve is not really changing the direction, it's still 1. Okay, and now the value at 2. The value at 2, we need the value above, this one, okay, plus slope, I mean the step size, times the slope. Wow, lots of ones. Negative 1 plus 1 times 1 is 1. It is simply negative 1. Okay? Value of the function at 2 is negative 1. Okay? I think you are an expert with the Euler's method by now. Thank you. Please join me for the next section. Thank you.